Okay, Assalamu alaikum all. I hope that you all are in great health wherever you are, working from home or studying at home. So we are live sessions about neural network of machine learning. What is this? What is it about? And how does it work? And how you can use it in your future and your work. So it's all discussed a lot of scopes by our new guest speaker by Alexander Manuel. He is the previous DSC lead in the University of Computer Indonesia, and he is attended as a top lead of 21 events in 2 months and has a great working experience in neural network of ML. So further goes on, we are introducing Alexander to So to start it, so you shall start the sessions. Alexander, please, back to you.
All right, thank you, Zara. All right, folks. I'm going to discuss about introduction to machine learning and neural networks. Probably some of you may have heard, or probably you never heard about that before. It's all right. You're gonna get there. So, a quick about myself. Wait. All right, here we go. A quick thing about myself. So, I was the previous specialist in my campus, university, the Indonesian Computer University, and I was the top CC lead on October to December 2019 in Southeast Asia with Prince. And this is my team. Here, I've held many workshops and collaboration with the other DSC in Bandung, West Java, Indonesia. I held Actually, we have 4 different classes, so we do 4 weekly classes like machine learning, Kotlin, and back end and front end. So this is my team. There are them, the heroes of the SU Lit, and also the Explore ML facilitator for the beginner and intermediate. So that's all about me. So what we are going to talk about is machine learning, the neural network, and we're gonna create a model. So, what is machine learning? So, some of you might heard that machine learning is something like an advanced robot, like Terminator, like something so advanced, so computeristic. Because it is, but it's not all of it. It doesn't explain the actual meaning. The machine learning is actually the brain, the core that actually learns the pattern of the data. So, some of you might seen this kind of Venn diagram, but probably some of you doesn't know there's this the second, the fourth, the thing that called representation learning. So actually, the artificial intelligence is part of the deep learning is part of representation learning, and representation learning is part of machine learning, and it's all part of artificial intelligence. So in terms of artificial intelligence, it's like what I say, it's as simple as program that has knowledge base. For example, if you know this program called Mycene for treating blood infection, it's actually back in somewhere 90s. And also, and the next step is machine learning, something more. When we introduce the application function, like this, the logistic regression, or maybe with the name sigmoid. And actually, there's this part called representation learning. This part is sometimes people miss this kind of part. It's the example, as you can see, it's the autoencoder. So you take an input and then you make a representation, a compress of the data of all the data set, and then you can encode it back, like you can see in the image here. And then the deep learning that we all love about, whereas the initial there was a single layer perceptrons, and then there's this multi-layer perceptrons. So that's about the machine learning stuff. And there's a thing that you need to understand, that our, like, what you learn, like app developing, it's almost all of it is rule-based system, where you put an input and then you hand design the program and then you can see the output. And the classical machine learning, there's this, you put an input and then you wiggle some, like, hand design the features, like your own features manually, and then you mapping it to some features, and then you can see the output. And then there's this whole box of representation learning. The the first one is, there's a, you put in it, you get an input, and then you get a feature, and then you map it, and then you get an output. And there's this deep learning where you take an input, but at first it will see only a simple feature at first, and then after that it goes more deeper into some kind of layers, like a filter. So it will abstracting the data. I'll explain it even further in the next slides. And then you map it, and then you take the output. So as you can see, the shaded boxes is indicating that the components are able to learn about the data, the pattern of the data. So that's actually what differentiates between rule-based system and machine learning. And so there's this, which approach you can use. So predicting salary based on age, actually, uh, a, a problem, use case that can be solved by machine learning, like regression. I'll explain more about the regression. So it's about regression. And then how about this? Processing online payments. Is it rule-based or machine learning? Of course, it is a rules-based, because maybe you can see, like, maybe you thought that, how about the fraud detectment? I thought it was machine learning. Yes, it is a machine learning, but processing online payments is quite rule-based, because you only take the card or the orders, and then you put into the order details, and then you get the payment, and then you send it, and so on and so on. So it's a rule-based. You can hand written it. Process and analyze natural language data. Is it a rule-based or is it a machine learning? It is a rule-based and machine learning. So processing NLP, actually, there's a constraint about that. When you actually can do rule-based grammar with actually much more flexible and easy to debug, and most likely has a likely higher precision, but it requires uh, an expert to make the rule. But when you do it with ML, you can scale it more easily, and you get higher recall, and actually will much better later on. But you need a training data that has focus with annotations. And in machine learning, you cannot debug manually. Like, if the machine learning, even if obvious it is false, you cannot say that it is false manually directly to the machine learning. And next, detecting face in the photos, of course, is machine learning. So what is machine learning? So machine learning is an algorithm, a brain that learns the pattern of data. So that's machine learning. Okay, so I believe all of you understand. I hope you can catch up with me. And the next is, what is neural network? So let's go back first to the history. Actually, in somewhere in 80s, one of the 80s, the machine learning already exists. The term called linear regression. The, so it was used to predict the planets and P growth, because in when the researchers doing the research for this type of problem, they see that everything on the universe is actually go back or regress to the previous situation, previous occurrence. So that's why, hence they called it regression. And after that few years, after many years actually, not a few years, there's a single layer perceptron where there is only one neuron that has activation function, which was only linear, not non-linear. It was linear activation function to predict like um, or function or and, but it cannot predict XOR function. So people leave it after that. And then 20 years after that, there is this neural network where how about we can add more neurons and then introduce the activation that can introduce about non-linearity in the function. So, and then they found out about the multi-layer perceptron, the simple neural network, which is actually can be exist on that year. Some like used to do something like today, but the lack the lack of data and the lack of computer powers is making the machine learning cannot thriving on that year. So we are very, very lucky to live in this kind of year where we can have this machine learning with a computer power. So that's the single multi-layer perceptron. So machine learning has some kind of neurons, which you can see the small dots here, uh, which actually work. So this square called layers. One layer consists of many neurons. Is actually filtering the data that we inputted, and then it goes on to the next layer, to the next layer, and give a result. So, and in that layer, there is one activation function. So, in every each layer has one activation function, and type of activation function is actually a lot. For me personally, I only use sigmoid, 10H, ReLU, and liquid ReLU. So what's that activation function? It's actually deciding uh, deciding if the neuron will fire the value or not. So will the neuron firing a value or only some of the value? I'm not, you can say this. It's better here. I'm sorry. So as you can see here, the X is actually the input like from the image or text. The X is the input, and when you put it for an example, if the X value is 0, the E to the power of minus 0 is 1, and then so the fired output will be 1.5 half, I mean, so it's 0.5, and it goes on to the next layer. That's for synchronous. and then the value. If the value of the input is 0, then it will be 0 again. So it will be not, you won't use that. But if the value is x, and it goes on like the chart shown here. So before we get to here, I want you to understand that the activation function is not something like a function. It's more like it's transforming the value of the input to certain numbers, something like that. So some people explain it like the if function, if it's not and not. You will see the illustration after this. Okay, I'm gonna explain a very simple tale of a neural network, how it goes and goes, how it works. So for this, we're gonna using an image as a use case. We're gonna classify an image of dog and cat and classify it whether it's a dog or is it a cat. Very simple use case, but it's crucial to know the process in it. So you take some image and you do some pre-process. What is pre-process? Pre-process is actually a process, of course, it's process that turn the image into how can I call it? Into a value, a single value, into series of value that I mean, like you cannot put the whole image into the neural network. It only can take one one channel of our input. So you squeeze it. So actually in pre-process there's like rescaling, cropping. You can only have one type of image size. So you have to rescale it and then you crop it if the aspect ratio is different, like center cropping or maybe the left side or right side cropping. And that's there's a series of things that you can do actually in pre-process. And then you squeeze it, flattening into this series of pixels that I said, and then you feed it to the model. So what the model see actually series of pixels. So and the model has weight, biases, and activation. The weight biases is that will determine how the model will work. It's like a combination of value of weight and will determine the output of the model. So there's a lot of going on here in the model where the value will be feed forward to the next hidden layer. So it goes, you can see the cursor. So feed forward to the next neurons and then to the next neurons and to the next neurons. And then in that hidden layer, there is this biases and also the activations. So the activations will determine whether that value, how much value will be forward to the next hidden layer. And the hidden layer goes on. You can use list tons of hidden layers actually. And then on the on the end of the neurons, all the hidden layers, there is this output layer where we average the total uh, weights to determine whether is it the possibility. So in this case, is we're going to use a binary classification. So whether is it not or yes, whether is it 0 or 1. So in the end, we use it sigmoid. So it will turn all the list of weights into probability that has value between 0 to 1. So that's the feed forward. After you feed forward, you at the first iteration, at the first epoch, the machine learning, the model surely will make a mistake. So that's why we need to check how bad the model is. This is it. So we call it cost function. It takes so all the weight, all the biases will be used as an input for this cost function. Cost functions can be varied. One of the simplest one is MSE, the mean square error. And like you can measure the differences, the distance between the prediction and the actual value. I'm a, for instance, the actual value should be one because it is a dog, but the real value was somewhere between 0.67. So there's this error value. And actually, there's a lot of this cost function. So the cost function only checking how bad is the model is. We haven't we haven't finding the value of the new value for the new weight. How we do that? How do we do that? We use gradient descent. What is gradient descent? Uh, so if you all have taken the calculus class, when you have a curve, uh, normal curve, when you need to know which point, which coordinate is the minimum value, you do derivative, right, of that function. So in this case, so actually in machine learning, we have this term of global minimum and local minimum. You can have not just simple curve, you may be something like this, there's this low curve where there's uh, actually quite low, but actually there is another more minimum value. So in this thing, we're gonna seek which direction. So gradient is actually showing the slope of how you direct it, how you find the right minimum. Is it to the left? Is it to the right? Is it minus or a plus? So the gradient will show you the the direction and so on. So, but it's not we don't stop there. So in this case, we see that we use the partial derivative of the cost function respect to the weight and also the partial derivative of the biases respect to the biases. And then there's this alpha, it's learning rate. So in this thing again, actually, it's less of optimization. Sometimes it's not like looking like that. But the simplest one, we only times the learning rate to the partial derivative of the weight or the biases. And then we got the new weights after that. So yeah, I'm sorry if it's a bit too much math, but this is a very crucial thing that you need to know that the gradient showing the direction. The gradient is a partial derivative of the cost function, respect to the weight and biases. And then after you understand that, it's because in some cases, in actual cases, there's a moment where you need to know the weight. I'll show you how it actually works. So we're gonna talking about the math. Uh, a little bit about the. So that's all about the math. And then I'm sorry. Oh, okay. Ah, I skipped the actual math. Okay, so back again. So you have to know that the gradient and how you update that, and then I'll show you the intuition behind it. So let's focus on the cat. So we have this term called backpropagation. So after we feed forward, we go back to update. Let's see. We've seen the uh, equation before. So if you want to find the probability of is it a cat, we times all the weights and activation function and also the biases with the loss function or the cost function. In this term, the loss function and cost function is the same in this term. And then as you can know, the model. So we go back to the cat, and as you can see that the actual input is a cat, and then the cost function has proved that you are wrong. The model has made a wrong decision. So the probability of a cat that 0.67 should be higher, near to the one. So we need to uh, escalate the value of the output layer of the neural network. So in neural network, as you can see, I actually shown you in illustrate you that in actual cases in neural network, actually they don't perfectly know that is it a cat ear or is it a cat mouth or dog ear. But for the sake of uh, more intuition, I'll use this. So bear with me. So when there's an input for the cat, specific neurons will have higher value. I mean, shown in the illustration, it has more blue color. Will have higher value. It means like that neuron indicates more of a cat. So we need to make it higher. How we do that? We increase the bias and also we increase the weight. So we need to increase that weight in order to increase the final output. Okay. And how do you do that? Using the cost function. How using the cost function and then the gradient will seek the right neuron will find the right neurons to increase the value. So we increase the weight in proportion to the acquisition function. So because you can see in the equation above, it's weight times acquisition function. So there's this law called that says neurons that fire together actually wire together. So something that fire together with high value, sometimes it's wired together. And it is shown that it is true that cat's ear and cat's mouth indicate that it is cat. If the image found that there's a cat's ear, probably it's a cat. If there's a cat's mouth, probably it's a cat. But something that can actually quite similar, like cat's ear and dog's ear, some species has similar in terms of visual. So sometimes the model will get confused about that. So in here we can see that actually the dog's ear has more higher value than dog's mouth. So it actually works something like that. On the other hand, we need to lower the dog's ear and the dog's mouth value. So another thing that we can do is changing the activation function. But in this case, we cannot change the manually change the activation function. Or I mean, like in terms of when you training, yeah, after you train and then you change the model, you can change the activation function directly. So we need to get a higher value of the cat's ear and cat's mouth, and then lower the value of dog's ear and dog's mouth. But it's not just that. Let's zoom out a little bit. There's tons of ups and downs that we need to configure. So if we only configure the cat's ear and cat's mouth, the model will only learn about cats, but we need to learn about the dogs also. So with this, all the ups and downs of value, we will we will sum the value and get the average of it for each value, and then you take all of it and you get the average value for the final result. So in the end, when we talk about the weight, it's actually some value that lives in the neuron. So what's important is the weight in the neuron. So this thing, you can see it's only simple perceptrons, only four neurons in hidden layer. You can have billions of neurons which have combination of weights, and that's actually what makes it beautiful and actually quite hard to understand. So in this case, you can see why I'm saying that you need to know the intuition of this is because there is a chance, there's a probability when a neuron will have a zero value. So this neuron can have zero value, and that's not good. I mean, like I mean, like every calculation is a computation. You need a computation resources for every calculation. I believe you know flops. So the more flops you need, so the more flops means the more computation power you need. So if you calculate something, blah blah blah, and you have many tons of equations, and then in the end it gives zero. I don't think it's good. I mean, like you waste some lot of computation power. So in this case, this thing can uh kind of it can can make the value to zero, like when you plus 0.5 and minus 0.5, the result will be zero. So that's not good. So in terms of that, we can use uh, series of methods like regularization or dropout. But we're not going to talk about that. But because there's another thing to talk about. The purpose of that regularization is or dropout is to penalize the unused neurons. Okay. So the next thing. So you've learned about all of this and how it updates the stuff. I want to introduce you. Allow me to introduce you here a lot of gradient descent. So gradient descent is a rule of updates, like I've shown before, the learning rate times the weight. So in terms of gradient descent, we have there's actually many rules. There's finally gradient descent or the momentum, the graph, add graph, and list goes on. And what people use the most is optimization. Adam optimizer. So in here, the equation is actually quite rough. Uh, I I happen to know this because and actually do the math for my final project for the DC GAN, which use Adam optimization, that I have to know the actual weight for that and the actual calculation for that. But you can skip this. So as you can see, it's much more rough. So the theta is the weight and stuff, and then you calculate the v hat t and the v hat t to calculate the VT first, and so let's go. So there's four variables, that is learning rate, and then beta one, beta two, and the epsilon. In actual cases, and when you create a model, actually the TensorFlow have provided a default value for the atom optimization, optimizer. I'm sorry, for the learning rate is 0.001, and it goes on. But there's some cases that actually you need to change that. Some cases, but let's stick to the default value first. So what is neural network? Sorry, all of you saying back there. So for me, neural network is sets of series of neuron that works together and then works together from the input value, and then after one epoch it will update from the mistake. So and then it goes on according to the number of epochs. So what it learned is the pattern of the data. So okay, let's create a model. Is the thing. So I'm not going to do a live coding here, but I'm gonna share you the notebook that I've wrote here. I'll see here. It's a full notebook here. I've put the explanation, all of it here. Maybe I missed some, and you might questioning something. You can contact me. So yeah, I'll share this notebook to you. So we use the Google Colab. Some of you may not don't know about Google Colab. So Google Colab is a very powerful uh, tool that we can use for machine learning. You can use a GPU for that. And it's web based, and you can access this everywhere using your Google Drive, and yeah, and it's the thing that really good is you don't have to set the environment. What is environment is you don't have to install the like TensorFlow and update it, and it's it's quite hard actually. I'm actually using Google Colab and also using my own engine to do machine learning, and sometimes it took me like an hour or more to update stuff, and sometimes there's this module that cannot work with this version of module, and that's it's gonna take some time. So yeah, you can use Google Colab for learning and also doing your real project. Okay, back again. So we're gonna use TensorFlow. Why don't use another framework? Yeah, there's another framework. Is this PyTorch? I actually use both of them. For me personally, yeah, TensorFlow is actually quite young for in terms of comparing to other frameworks, but they are already doing a lot of things in their early age. It's much easier to deploy the model into web-based app or maybe to Android compared to like PyTorch. And one other thing is it's Google. Yeah, so it's really powerful, and then most of the people are learning it also, and you can find a lot of pre-trained model and tutorials in the website, and it will really help. So you don't start from scratch when you want to run TensorFlow. So that's TensorFlow. It's easy to implement the TensorFlow, and this we're gonna just put import TensorFlow as TF. Why TF? Because everyone doing it. You can use import TensorFlow as torch. It's, you can use that, but people will confuse. And then from TensorFlow package, you import Keras. So Keras and TensorFlow is working together. They usually, they used to don't work together, but right now they work together. And then in here we import not all the library, but we import the thing that we need actually. So we import layers, and then we import models, sequential. What is sequential? Well, you will see what is sequential, and then from layers you import dense and flatten. What is that? You will see after this. Okay, so what we are gonna do first is preparing dataset. I'm like after the TensorFlow thing, we prepare the dataset. In this case, we're gonna use two types of dataset. As this training dataset, it is the sample of the data that used to fit the model. And then there's this validation dataset, sample of dataset that the model haven't seen before. So it has to be different kind of data. What it does is actually like the name, to validate. So after one epoch of training, the model validated, will be validated using validation dataset to measure how good it is. Because it's different to, for instance, like you learn in school, 1 plus 1 is 2, and then 2 plus 2 is 4. And then after that, you get a small test, not a final test, but a small test, and that will show how well you understand the plus uh, symbol. Like first you sum 1 plus 1, the small test will be like 20 plus 20. So for us human, it's easy, but for machine, it's not something like that. They, even though it's obvious, back again, even though it's obvious, they don't see the things like we see. So they have to learn, and they have to fail and learn and then succeed. So in this term, uh, this is an example, not the actual performance. An example where the validation is score below the training means that they know basic plus 1 plus 1, 2 plus 2, but when the numbers increase, they got confused. What is that? 20 plus 20, what is that? So that's the accuracy. And then the loss is how bad it is. It's really bad. Even though it scores really good in the training, but actually they, they don't know about that. Okay. So when the training accuracy and the validation accuracy, I mean, when the training accuracy is high and the validation accuracy is low, you will have an overfit problem. So overfit is when the model actually, if I have the image here, oh yeah, I have the image. Yeah. So overfit is when the model actually, they know, they're remembering the data. They're remembering the data, not actually learn about the pattern. That's overfitting. When, yeah, the situation, when the chart, the definition of that is, can be explained by the chart actually. But for an intuition is, so the overfitting is actually when the model learns the data, remembering the data, but doesn't know the pattern of the data. That's overfitting. Underfitting is when the model doesn't learn anything. They don't know anything. So the thing that we're looking for is appropriate fitting, where even though there's some mistakes like this, it's okay as long as you know the pattern. Why we need to know the pattern is to know the no, I'm sorry, to predict the next kind of problem for this. So when you know the pattern, you know how to predict. So predicting something is something that haven't happened before. So if you only remembering the data, you will miss this kind of thing. For instance, when this circle go somewhere in here, it will be it will be missed by the model. Okay, so that's about the data set. We're gonna create the model. So the model actually is simple enough. It's quite powerful enough and simple enough to be used. So like what I've said before, we're gonna flatten the not flatten the curve. I'm going to say that flatten the input of the image. First the image is series of pixels. You put it into one channel. Even though the image have three channels, you put it into one channel, and then there's this image shape. What I said, you need to define the actual image shape. And then after that, we put a dense layer. Dense is series of neurons. So in this case, there will be 200 neurons with the attribution value for the first layer as 200. So you've seen like 5 neurons. Right now you're using 200 neurons. And after that, we're going to use 60 neurons with value. And then the output layer, 1 neuron, going to use sigmoid to output the binary classification 1 or 0. So that's how you made a model. You can use as many neuron that you feel like you need, or as many layers that you need. But it depends. Back again, it depends on the power of your computation, on your engine, or the time that you will provide for that. The more neurons, the more computation power and time that will take. So for this, for this simple model, we're gonna have somewhere within like 15 million, right? Yeah, parameter. And it's only a simple neuron. Imagine a large scale model that has series of neurons and layers. But this thing is quite good enough. Quite good. And we'll see why I say that. Why I say something like that. So after that, this is the summary. After that, we fit the model. We use the training data set, and then we use the epoch. How many uh, how many times that will all data set will be used, and then the validation, we're going to use the validation data set. So it goes on and goes on. We'll print something like this, and then you can plot some charts. In this case, it's actually, uh, yeah, it's around 60%, and it's good. It's not everything, but it's under 15. So there's a problem. Uh, I don't want to say it's a problem, but there's something that we don't get. So the model is actually, uh, they learn enough, but they don't know enough yet. In this case, it's obvious it's a cat. There's no other thing around it, a human or maybe something furniture, but it fails to predict that it is a cat, and then this one is quite low for a dog. Why is that? Um, how do I improve this thing? Is it more data? Is it data augmentation? What is that? Data augmentation is simply it's like you rotate the image because uh, it tends to behave differently when you uh, so if in our human eyes it's really good. You know whether is it your friend or not, even though it's from behind or from the side or from the front. You know that that is your friend. But in machine learning, when you only show the picture of one picture, they don't know if that is a cat if you flip it or you rotate it. That's the catch. So you can do some data representation where you rotate or flip and stuff. But is that the answer? Or maybe better models at or hyperparameter tuning. Hyperparameter is something like epoch, hidden unit, layers, resolution. So should we have more epoch? Should we have hidden unit or layers? So that's a question that you should answer. But let me explain something. So the problem is the neurons. Why it doesn't recognize that it's cat is because it receive it receives an input that is really abstract and uh, you don't know the correlation. You know causation and correlation. So when this gets into the model, you can I explain it again. The pixel is one by one getting to the model. So the correlation between these pixels up here and then this pixel down here is hard to be learned. It's quite hard. So there has to be something that can be the solution for them. I wanna spoiler a bit. It's actually called CNN. That's for another topic, but for spoiler, actually CNN, there's this thing that called feature extraction. Yeah, just like what it says, feature extraction. They extract feature like the ears, the eyes, and stuff, and actually can improve the model. But is the CNN is good enough? It's 2020. There's something more, right? All right. So uh, that's all for me a bit for this session. So you can improve this thing by actually you can improve by adding maybe neurons, but don't too much, you will break your machine. And but there's got to be there's another solution, and for that, if you want to find it yourself, you can learn more about here. Like if you want to know about gradient descent, I will share this presentation on my speaker deck. I will share the link to Zara, and then the link. And there's this book that I highly recommend called Deep Learning called Ian Goodfellow. Why I choose this book is so Ian Goodfellow is the father of GAN. If you don't know what is GAN is, Generative Adversarial Network. That's my final project actually. It used something like that similar to they make the architecture model, the neural network model that look like an autoencoder. So it's not just decode, compress the data, but it also encode. So it can generate from the compressed data, it can generate data. So that's really amazing. So it's really smart. I recommend you to read that book. It explained the algebra, all of it in the first chapter, and then the second chapter says more into the machine learning stuff. So it's like one in all package if you don't know anything about math and also the machine learning. And also another book for more practical, it is Hands-on Machine Learning by Arilyn Giron by O'Reilly. It's very good. There's a lot of code there. And maybe if you more into the practical stuff, you can visit this tech dev guide with google.com machine learning. And there, so just like the name, there's a lot of guides that first you will have to finish the ML crash course. It is a really, really good course. It covers all the important topics. And also after that, you will be guided into the series of Kaggle competitions and also uh, Dataset. So for some of you that don't know Kaggle is in Kaggle you can find a real world ML use cases with their datasets and also the notebook. So if you don't know anything, you can see how people use that dataset on on the code. So it's like you can learn anything there about machine learning, like reviewing other codes and comparing one people code and then comparing one another, and then you find a really, really good one, and then you understand. And when you don't understand about the basic, you can go back to the theory, to the book and stuff and stuff. That's how actually I learned about the machine learning. More to like simple and self-guided. So this is the thing. So that's all actually from me. I hope all of it, all of you can understand well, and then can get more things, can get a lot of things, and understand more about machine learning and neural networks. And I'm really sorry if I made a mistake, or if I find you find that I say something bad. I'm really sorry, but yeah, I'm human. So this thing what I made during my high school, I'm sorry, during my campus time. This the thing that I call the GAN. It generates from the noise value. This one is deepfake, and this one is Dolly. It's made by machine learning, not some video editing stuff. Machine learning, you do this. And mask detector, and this one is I deploy it actually on Firebase for my mini project for the campus project, the small project. So, like what I said, I use TensorFlow to deploy this. You can find the code on GitHub. Uh, so you just need to export the model and then put it on the web. I believe all of you know how to make a simple HTML and CSS stuff and a little knowledge of machine learning, and then you can deploy your model. Sounds good. So that's all from me. You can feel free to connect with me on lexmanuel.com, on my LinkedIn and twitter.com. And I'll share the speakerdeck.com, this slide on speakerdeck.com/lexmanuel. All right, that's all from me. I give it back to where is it? Here. All right. Uh, you haven't unmuted your microphone.
Okay, sorry, I didn't notice my mic was unmuted. Okay, so thank you so much, Alex, for this session. Very great knowledge. I hope the students will learn something from it. So there's a question. I will make it publish. I think this someone wants to say it. Okay, this is the question.
All right. So I answer it now, right?
Yeah.
Okay. So if a neural network identifies an object as cup, recognize another cup with another shape as a cup. So it depends. Sorry, it's not yes no question. It depends. If the cup actually, let me show you. I have series of cups here. So this thing is a cup. Some say it's a cup. Maybe other people say it's not. This one is cup, but it has similar pattern. I mean, like it is a tube. So maybe in most cases, because I believe the neural network will know it is a cup, but there's even low chances it actually don't know that it is a cup. So like what I say, it depends on the back again. It actually depends on the quality of the pictures and depends on the lighting and stuff. So to answer that, yeah, I believe it will recognize it as a cup, most likely, but there's another probability, a low probability that we will recognize as not a cup. Thing. Okay, thank you for the question, Alex Costa. All right,
Okay, thank you so much. Thank you so much. And those people award the uh, this presentation session. I will send it to the whole people who have registered through the email. Okay, Alex. So you can send me to the email this slides, and I will
sure.
send it. Okay. So thank you so much, all. I hope you learned something
Thank
great.
you.
Best of luck for the future. And thank you so much, Alex, for giving your precious time, and so the people have learned something here.
Thank you. Thank you.
Okay. So that's all. End of the live session. Thank you.